Vice President of IASTA. IASTA is Indian Aerosol Science and Technology Association. And welcome to the lecture number 21 of the IASTA lecture series. So let me tell you a little bit about the IASTA and the IASTA lecture series. So IASTA is a professional organization for scientists and engineers who are striving to advance aerosol research in Indian context. The association provides a platform for exchanging knowledge and resources. It spreads information among researchers, member organizations, industrial counterparts, and related disciplines by organizing conferences, technical meetings, lectures, and publications, etc. IASTA addresses various interests such as environmental science, air pollution, indoor air quality, occupational safety and public health, industrial and medical application, and nuclear safety, etc. IASTA is a member of International Aerosol Research Assembly, which is IARA, and Asian Aerosol Research Association, AARA. We started this IASTA lecture series in April 2023, and our first lecturer was Dr. Y.S. Meyer, and now we are at 21st lecture. So in this lecture series, what we do every month a lecture, which is online for about 45 to 60 minutes. It is by an eminent researcher working in various fields of aerosol research in science or engineering or medicine or industry. The lectures are followed by interactive session, question answer by students or whomsoever wish to ask. Today's speaker is Dr. MingzhouYu from China. And to introduce the speaker, I would request our Dr. Y.S. Meyer to kindly introduce the speaker. Sir, please.
Good evening, friends. Thank you, Dr. Rastogi, for giving me the opportunity to introduce Dr. MingzhouYu. He is a very eminent aerosol theoretician in the world, and he is a very prominent member of the Asian aerosol science community too. He is really responsible for initiating a very important activity in the area of aerosol modeling. And as all of us know, population balance technique is one of the most prominent tools in addressing aerosol evolution dynamics. Population balance is applied not only for material generation, material synthesis, but also in environmental science, and of course in a host of other disciplines, not necessarily or beyond aerosols. There have been several methods for solving these population balance equations, which are very complicated, they're very nonlinear, and precision is very important. Of them, the so-called moment methods, there are divergent methods. Dr. Yu initiated what is called as the Taylor expanded method of moments for specifically addressing the coagulation aspect of the population balance problem. He has been persistently following it for the last 20, maybe 15 years or so, coming out with the scores of publications I am aware of. Many co-workers from China and elsewhere in the world have followed his techniques, and I'm quite aware of the large number of citations. Among the theoretical work, it's not so easy to get citations. He has got large citations on his work also, and it has been applied now for various contexts. So his major research interest, basically, as far as I understand, is on this application of TMOM methods, which he has applied to nanoparticle synthesis, measurement techniques and dynamics, and also he has incorporated fluid dynamics methods in additionally, depending on the problem in question. He has some of his papers on multi-phase flows incorporating this TMOM method have really been an outstanding contributions to the subject. He, as of now, I read that he has about 100 publications, and he has written in books. He has patents, because he, apart from his PhD theoretical programs, he also has many MTech programs. He trains students and conducts experimental studies. He is one of the leading aerosol scientists in the laboratory, supported by the Zhejiang Special Provincial Support in China Jiliang University. On a personal note, I had the good opportunity to know him way back in 2010 when Professor Gerhard Kasper, at that time in Karlsruhe, was hosting him as I think a postdoctoral student, and we had a inter-country collaboration between Baba Atomic Research Center with me and Karlsruhe with Professor Casper, and then Professor Yu worked there along with Professor Seipenbusch. So we, myself, Anand from here, and we really addressed a very important problem in particle evolution and coagulation, and that is when I first came across his contributions in handling it. Ever since then, he has been continuing to work and address, and I had the good opportunity also to visit him in uh, Shanghai, in his city in the China Jiliang University in Hangzhou. And of course, it's a very beautiful city. And we are together discussing many problems and many aspects. That was also the beginning of our air cleaner. I mean, with him, we visited the great air cleaner that was built in China, and that was the motivation we received. I'm also myself and my wife. We know his family. His wife with a beautiful son and very happy family. And it's a pleasure to have him. We have done a good job. We have done. I really thank the organizers for inviting him to give a presentation on his basically moments method, Taylor expanded moments method and its applications. With this, I invite Professor MingzhouYu to deliver his speech on the topic of his interest. Thank you for accepting and joining us. Please welcome Professor MingzhouYu. Thank you.
Thank you. Thank you, Professor Maya. And so next, should I share?
Yeah, please share your presentation.
Yeah. Okay. It's okay?
It is opening. It is
not
opening.
yet.
Now it is open.
Not
Yeah.
okay.
Yeah, please start. Yeah.
Okay. So, okay. Good afternoon, everybody. Friends. So, from my side, it has been night, but I just say so. It's dark outside. I guess in India, it is still light. So, I'm MingzhouYu, came from China Jiliang University. Just now, Professor Maya told everyone, and so my hometown is Hangzhou. It is a very beautiful place, and here many thanks to Professor Niraji Rastogi. I hope my pronunciation is right, and Professor Ananda and Professor Maya for the invitation, for giving me the opportunity to present my work on this important platform in the Aerosol Science and Technology Association. In China, and unfortunately, we only have the aerosol community with and the Chinese Society of Particulology. And thank you, Professor Maya, for the kind introduction. I still remember the time you visit our university, and greatly appreciate the research guidance you provided to me and my student. And thank you, Professor Anada. And we have a good cooperation guided by Professor Maya and Professor Gaspar and Seipenbusch. I still remember, so it should be 13 or 14 years ago. So we just talked very long time ago, and but the time passed so quickly. Today I will speak on the message for modeling poly-dispersed particle flows. I approach based on the populist balance model for simulating poly-dispersed matrix flows. This is the outline of my presentation. First, I will discuss the background of poly-dispersed matrix flow and population balance modeling. Second, I will present themes for closing the moment equations with a message for solving the Bohr calculation equation. In this talk, I will introduce 4 methods of moment. The Taylor series expression method of moment proposed by our research group in 2008 when I studied for my PhD degree in Zhejiang University, also a long time ago. So, the method of moment with interpolative closure originally proposed by Professor Frank Lanke in 1987. Building on his work, we have further developed an improved model. The inverse Gaussian distributed method of moment and the gamma distributed method of moment, both developed by our research group. And I and my colleague, Professor Singh, in my university, we together did this work. Now, I give the introduction of my talk. Poly-dispersed matrix flow are actually around us and show up in different areas. For example, you can find them in droplets and bubbles moving through turbulent flows, in ocean spray flow accumulation process, in rivers, and in aerosol dynamics. Also, I want to show my research made about aerosol dynamics. You might see particles, droplets, bubbles, or even cells in dispersed phase. The defining feature of those systems is that they are poly-dispersed, showing a spread of size, velocity, and other physical quantities. Let me use clouds as an example to explain poly-dispersed matrix flow. If we want to understand the large scale evolution of clouds, how they change, and the mechanism driving that evolution, including the impact on climate through aerosol cloud interaction, we need to focus on scales as small as nanometer and micrometer. At those scales, the dynamics are dominated by tiny droplets and aerosols. And the process at play includes calculation, condensation, gas to particle conversion, and interaction between particles and turbulent flows. Similar dynamics are also at work in chemical engineering process. This work, when I worked in Karlsruhe Institute of Technology, my mainly work about chemical engineering science. The challenge in poly-dispersed matrix flow are the multi-scale nature, the interplay of diverse dynamic process, broad size distribution, and above all, the variety of the particle number density focusing. When we rely on numerical simulation, we need a single modeling framework that can handle all of those issues together. That's exactly what population-based modeling works. We usually decide which type of multi-phase flow model to use by looking at two things: the Stokes number and the particle volume fraction. For poly-dispersed multi-phase flow, we are often dealing with very small Stokes number and very low volume fraction. In this reason, the focus is mainly on particle dynamics, process like gas to particle transform, particle growth from calculation, and aggregation. And of course, if the system involves turbulent flow, we also need to consider the interaction between turbulence and particle dynamics. As a numerical modeler, what do we want to know? We want to find out how many small particles, droplets, or bubbles there are after a certain period of time, and what the size distribution looks like. If we want to describe this process mathematically, we use a population balance equation. In this equation, n is a function of time, position, velocity, and particle property, just like size. The process can involve particle growth, coloring, nucleation, and breakage. In this presentation, in this talk, I will focus the problem of coloring. Here, we focus on binary coloring. In most aerosol systems, the particle volume fraction, just like I talked earlier, is so low that only two particle coloring occur. When two particles meet, they collide and merge into a single particle. As a result, the total number of particles decreases, but the overall particle volume or particle mass remains consistent. They does not change. We extend our discuss to a system containing many particles. In such a system, it is impossible to track every individual collision event. Instead, it is more practical to determine the property of collision occurring throughout the entire system. For this, we need to know how many collision events take place overall. This is described by the collision canal, just like this one. The collision canal can be derived using fixed diffusion theory and gas particle molecular dynamics. For the binary coloring process of a system, the first work, I guess everyone now, came from Mary Smolensky. He first gave the equation to describe the process. It was later called by Brown calculation equation or Smolensky calculation equation, describing the time evolution of the number density of particles as if. Strictly speaking, the Garvin equation in subsequent population balance modeling, the population balance equation or general dynamic equation, derives or comes from the Smolensky equation. So yesterday I just checked from Google Scholar. So it is more than 1,500 results. If you check Smolensky calculation equation, so it is worldwide by aerosol scientists. The Smolensky calculation equation was later revised by Mueller in 1928 for its integrate differential form. Here, beta is the calculation canal. Next, I will introduce the solution of Brown calculation equation. I have just introduced the Brown calculation equation and discussed its mathematical structure. Due to the presence of calculation canal, this beta, the equation is a highly nonlinear integrate differential equation. For simplification, scientists often treat beta as a consistent, in which case the equation can be solved analytically. Unfortunately, when beta is the true physical canal derived from diffusion theory or gas kinetic theory, the Brown calculation equation cannot be solved analytically, just like this form and this form. Addressing this challenge is the focus of our work. Since the equation was first proposed in 1916 by Professor Smolensky, several solution methods have been developed, including the Monte Carlo method, the method of moment, the Sexton method, and even the application of AI in recent years. So from, I think about 3 years ago, one of my students also used AI for the solution of this equation. Each of those approaches has its own advantage and disadvantage, depending on the specific application. In our work, we mainly used method of moment. For me, I mainly use the method of moment, but for my students, they have changed to AI for the solution of this equation. I want to highlight why the Brown calculation equation focuses on particle number density, referring a quote by John Attingen. In 1808, he recognized that in system composed of small particle number density plays a very important role in determining the system process. This insight, I guess, may be one reason why Professor Smolensky later formulated his Brown calculation equation in terms of particle number density. Before I discuss how to solve the Brown calculation equation using the method of moment, let's first review the classic multi-phase flow models. The traditional Euro approach deals with two-phase flows by applying volume or assume average. However, I think this method is not suitable for poly-dispersed system because key physical quantities such as particle size and velocity are averaged out, causing important details to be lost. To address this limitation, a promising approach is to establish a mass equation for the particle number density function. Follow this way, then by applying the method of moment, we can achieve closer and develop an improved Euler model. Following this idea, if the internal variable is velocity, the mass equation we just talked for number density becomes the kinetic equation. if the internal variable is a particle in number, particle size in the number density function, it becomes the population balance equation. The latter is widely used in aerosol science and technology, atmospheric science, and also chemical process engineering. In this equation, if the source term, this is source, if this source term include Brown calculation, only Brown calculation, and we neglect the convection, growth, and diffusion term, then it is reduced to Smolensky calculation equation. If both particle size and velocity are function of number density function, then we call it generalized population balance equation. Whether it is kinetic equation or the population balance equation, they cannot be used directly for numeric calculation due to their very high degree of freedom. Therefore, our goal is to reduce this complexity. The most effective approach is to convert the number density based equation into moment based equation. Unfortunately, this conversion is not straightforward as it involves both spatial-based clause and dynamics-based clause. This is the challenge. We have to solve it. Several clause schemes have been developed for number density-based equation using the method moment. Those various approaches are now employed.
Is the slide not moving? Hello?
Not
I don't know
moving?
if you're. I don't know which slide you are showing now.
Did
Yes,
you
sir.
see?
Slide is
Now?
Because I
Not
see only
moving?
one slide for a long time in which Smolensky's picture is there.
Oh, I try again. Yeah.
yeah. That's it is empty. That screen is empty here.
Sorry.
There is no
So
presentation.
I can see the slide.
But I saw one slide
Now
frozen for a long
presentation is not
Yeah,
there.
now it is not there. Yeah. Or maybe it's my problem, so you can continue. But
Sorry. Can you see?
yeah, we can see the slide. Please
Yeah.
roll over. Yeah.
Not work?
No,
Yes.
keep moving, and
Keep
go to
moving.
wherever you were there.
Yeah. Beyond this, I didn't see.
Yeah.
Here?
Last I saw this slide, please.
Okay. This we didn't see. Yeah.
From here? Okay.
Yeah. Okay. Now it's visible. Yes.
Okay.
Yeah.
Okay. Okay. So I just introduced the Brown calculation equation and discussed its mathematical structure. Due to the process of calculation, this one, beta, the equation is a highly nonlinear integral differential equation. For simplification, scientists often treat beta as a consistent. In this case, if it is a consistent, the equation can be solved analytically. So, it's moving. Hello?
Yes,
Yes.
it is
Yes.
moving. Yes.
Now moving. Yes.
Okay, so I'll continue. So, but unfortunately, when beta is the true physical canal, the derived from diffusion theory or gas kinetic theory. This is from gas kinetic theory, and this one came from fake diffusion theory. The Brown calculus equation cannot be solved analytically. Addressing this challenge is my work. Since the equation was first proposed in 1916, several solution methods have been developed, including Monte Carlo method, the method of moment, the second moment, the second method, and even the application of AI in recent years. Each of those approaches has its own advantage and disadvantage, depending on the specific application. In our work, we mainly used the method of moment. For me, I mainly used the method of moment to solve the problem. But for my students, that's what I talked earlier, and they have moved to another direction. They more like AI to solve some problem. So this is the difference between older professor and a young student. Okay. I want to highlight why the Brown calculus equation focuses on particle number density, referring a quote by John Attigan. In 1818, he recognized that in a system composed of small particles, particle number density play a very, very important role in determining the system process. This insight may be one reason why Professor Smoluski later formulated his Brown calculus equation in terms of particle number density. Remember, before discuss how to solve the Brown calculus equation using the method of moment, I want to review the classic multi-phase flow models. The traditional Euro approach deals with two-phase flows by applying volume or assume averaging. However, this solution is not suitable for poly-dispersed system because physical quantities, very, very important physical quantities, such as particle size and velocity, are averaged out, causing important details to be lost. To address this limitation, a promising approach is to establish a master equation for the particle number density equation function. Then, by applying the method of moment, we can drive closer and develop an improved Euler method. Following this idea, if the internal variable is velocity, the master equation for number density becomes the kinetic equation. If the internal variable is particle size in the number density function, it becomes the populus equation. The latter is widely used in earthshow science and technology, atmospheric science, and chemical process engineering. In this equation, if the source term unknown include Brown calculation and we neglected convection, diffusion, and the gross term, it is reduced to Smoluski calculus equation. If both size and velocity a function of particle density function. So then we call it generalized population balance. Usually, the freedom degree is beyond 2 dimensions. 8 dimensions. Whether it is the kinetic equation or the population balance equation, they cannot be used directly for numeric calculation due to the very, very high degree of freedom. Therefore, our work is to reduce these degrees. The most effective approach is to convert the number density-based equation into moment-based equation. Unfortunately, this conversion is not straightforward because it involves both spatial-based closure and dynamics-based closure. This is the challenge for our work. Several closed schemes have been developed for number density-based equation using the method of moment. Those various approaches are now used by different research across different fields. This is my professor. So he now worked in Zhejiang University. The first widely used method of moment was the log normal method of moment. With this method, assume the particle size distribution remains log normal at all times. Today, the most commonly used method are the quadrature method of moment, this one, and its direct quadrature method of moment. For this method, this kind of method, the number of equations is twice the number of variables, requiring large metric computation. In our work, we instead use a Taylor series expansion technique to close the equations. An approach, we call it TEMOM, team method. In 2020, our research group also proposed a new method of moment. We call it inverse Gaussian distribute method of moment, whose closed function is this. I will describe this method later. Regardless of whether the quadrature-based method of moment or our own method is used, the key to the implication lies in constructing a proprietary closed function for arbitrary moment. Additionally, any method of moment should have the capability to reconstruct the size distribution from the low odd moment. Just like this, for every method, we should ask them, they should have the ability to reconstruct the size distribution from the moment. Now, I will introduce several themes for the class of moment equations. Mary Smolutsky was the first to study calculation problem. Just now, I have talked this. And he first gave the Gavin equation about a process. We call this equation Smolensky equation, and his idea for the study, we call it Smolensky mean field theory. An important variable in Brown calculation equation is calculation canal. In different size region, it has different mathematical form. They are apart from different theory. This is the number density based equation, and the internal variable is particle volume. To convert it to moment-based equation, we need multiply the number k to the power of volume v. Here, beta, this one, beta is the calculation canal, and then the task is to find a way to remove integrate operator. We need to remove this one. If we use Taylor series to deal with some unclosed term, we can convert the Brown calculation equation to a system composed by those equations, but it is not closed yet. You can see just like this one. When the calculation canal is introduced and the integral is evaluated, we obtain a set of ordinary differential equations, just like this one. Unfortunately, those equations contain very many implicit moment variables, resulting in a lack of closure. Therefore, our work is to find a way to replace or to remove those implicit variables, just like you can. A lot of, we cannot get the closure of this equation. So next, how can we do? Our idea is to expand the number k, the power k to the power of v using the Taylor series expansion method, and then we can establish a closed function which is a polynomial in integer moment. We can adjust the closed function by varying the reserved order of Taylor series expansion. This is the third order. This is the fourth order. So different Taylor series, different series order, we can different closed function. However, for any Taylor series expansion, we must give its point of expansion. For this problem, what is the point? This is the key of this method. We tried to use the mean variable of the system to be as the expansion point. Here, if the internal variable is volume, the mean value of particle volume of the system should be this one. We also have a try to use the geometric mean value of the system, but it is not an idea. It is not a good selection. We do not know why. Maybe it is a mathematical problem. Once the expansion point is given, the final moment ordinary differential equation can be obtained. Here, the number density function-based equation becomes to the moment-based equation, and it is very, you can see it is very simple in mathematical form, and especially a variable are explicit. Thus, it can be solved numerically using common ordinary differential equation code, ODE code. This is the work we did in 2008. This is the work when I studied for my PhD degree very long time ago, 2008. So, and now this method, we call it team method. As compared to conjure based method, compared this method and logonomic, this is logonomic method. The team method shows very good accuracy. And so this is also the comparison for geometric division. So it is also very good. To validate the method, we also compared a method to other recognized method, including sectional method. Because of the property of explicit variable and simple mathematical form, the team costs least computational time among all the invested methods. Of course, its accuracy also can be ensured. So you can say, so the different methods give very similar the result. Regarding team, Professor Xie Minliang from Huazhong University of Science and Technology, also in China, conduct an error estimation and validate this method is a good one. His work published in Also Science and Technology. The team has first developed for several aspects, including canals, multi-model, multi-dynamics, engineering applications, and multi-component. Since this method was first proposed by me in 2008, there have been several class functions within the framework of a team, including other research groups. Two groups, Professor Asho from USA and Professor Lu group from China, also proposed variant method for to deal with two-component system. If we try to solve the poly-dispersed system as enough to approach the real problem, we have to establish the governing equation, just like this one. This is an equation with a degree more than 7 dimensions. Direct computation is not allowed. For this, we can use TMO1, the team, to deal with it. We can use our method to deal with it. Usually, we separately deal with those dynamics. We did this because we want to publish some papers, because we have to separate it. So different aspects. I give some examples. Use this method. This is the problem related to laminar or turbulent shear calculation. The flow make all the small particle closer and then closer to become big particles. We can use TMOM team to obtain the governing equation for total particle number concentration, mass concentration and the second moment equation. We only need to solve those three equations system. So this problem also was first studied by Professor from the Linde. This is the condensation process. Professor, sorry, I want to know. So, how many time for me next? Hello?
Yeah, means 5 minutes.
5 minutes?
Yeah.
Oh, I saw it quickly. Oh, okay. Sorry. Okay. I scroll quickly and okay. This is the condensation problem and okay. This is the brackets and this is the diffusing process and so this is the analytic solution of Smolensky equation. So this problem was first studied by Professor Blandet and Professor Lee. So I give some solution using team. Okay. So this is the example. Also examples using method. Okay. And we also studied the time to reach the self-preserving size distribution. So this work also studied first by Professor van der Linde and Professor Lee, and also so Professor from America also uses this method, and they developed it for a two-component system. Okay, so this is the work by coupling Team and Navier-Stokes equation for turbulent problem, and also we apply this method for calculate aerosol formation and subsequent for exhaust. Okay, this is also our work published in GGR and also for the gas occupation. Okay, because of the time, so I think maybe now it's okay because I have more PPT, but maybe next time or maybe in India when I attend the conference, India Aerosol conference, I will present my presentation. It's okay, Professor?
Yeah, if you want, this 2-3 minutes you can take if you want, but if it takes longer time, then maybe
you can summarize. Maybe you can summarize your study.
Yeah.
Okay.
Yeah.
Okay.
So you can go.
Okay. This is the conclusion. So I think the team is a general tool for resolving for fine particle fluid involving particle droplet bubble calculation, catalysis, nucleation, brackets, deposition, and I think this method may be used by different process, just like atmospheric process and chemical engineer process. So okay, and this is my city. So I just checked from internet. So Hangzhou is a very beautiful place. Welcome everyone. Come to Hangzhou, visit our university. Thank you very much. Thank you all.
Thank you so much, Dr. Yu, for interesting talk. Now I would request Dr. Anand, to please continue with the question answer session. Dr. Anand, please.
Okay.
Thank you very much, Dr. MingzhouYu. We will request the participants if they have any more questions. Online participant, please raise your hand.
Professor,
You can directly ask the question.
Professor, another, I guess maybe your voice is low.
There's some echo somewhere.
Uh, uh,
Yeah. The participants can ask if they have the question or they can type in the chat box, please.
mhm. Which one?
Yeah. So in the meantime, I can just ask him one question.
Yes, sir. Yes, sir. Please.
So Professor MingzhouYu, I
Professor
have a
Maya? Yeah.
yes. Mine is not a big question. I was quite interested in seeing your application of your method to the shear coagulation problem for the
Thank you.
Friedlander's shear kernel, for Friedlander's kernel, right? The
Mm-hmm.
shear.
Yeah. He did it very earlier.
I had not known
Yeah.
that. It is so. Do you get good convergence in that problem?
Mm.
Do you get accurate reproduction of the evolving size spectrum?
We can wait because they work and they have some assume they assume particle size distribution is consistent. So
Okay.
yeah, and
Because there is a very strong kernel. Yeah.
and this work also later did by Professor Lee. I guess you know him, and yeah, he also did some work, a lot of work for this problem. And but Professor Lee also assumed the particle size distribution always follow log normal distribution. So and we can use the team to solve this problem, and because you know, and the team without any physical assumption. So and we compile the result. So they fit very well. I think it is okay. Yeah.
Okay. Yeah. My question is over, Anand.
Mm.
Yeah.
Thank you.
Okay, sir. Thank you.
Okay. I guess Professor, and if someone have question, and they can send me by email or yeah.
Yeah. One more
And
question. Yeah. Slide number 25. So,
okay.
sir, one more question. Whether these equations are even some tried with the coupling with the advection diffusion equation, like coagulation equation plus advection diffusion coupled equation, whether somewhere it is tried with the temom or cumom.
Sorry, sorry.
You
I
you are
I
not
I can
audible.
I
Dr.
cannot
Anand,
hear.
is the
Yeah.
person with
Uh,
you, he's not audible properly. Please, can you
uh,
please ask him to
uh,
come closer to the mic and then speak, ask the question, please?
Yeah, please.
uh,
Sir, this diffusion audible.
uh.
Sir, whether
Or maybe you yeah. uh,
whether if I couple the coagulation with the advection diffusion, whether somewhere we can use the temom or the tumom for solving the
I think
coupling
your
or
voice is
You are
breaking.
not clearly audible. You are not clearly audible.
Maybe
Not audible.
you write your question and send.
uh, I guess it's better for you to give me a message. A message. Oh, yeah, yeah, of course. Yeah. Oh, oh. Is it possible to solve a couple? Yeah, yeah. The team can be used to solve calculate the vacuum and the diffusing. So we only need to cap it to noise equation. That's like this one. Yeah, this one and yeah, this this is also the turbulent flows by coupling the team and the noise through equation, and also this one. So this is the particle phase, and also we need to couple this equation to noise through equation to solve the problem involve particle dynamics and flow convection and diffusion. Yeah, yeah, yeah. It is the same. I think it is the same as a quarter a method of moment. It's the same. It's the same. Yeah, yeah.
Yeah, thank you, Mingzhou. Are there any more questions actually
Mm.
from
Sorry.
participant from YouTube channel? As well, can post the question in the chat box.
Mm. Professor, another. I think. Would you please give me a message? Message.
Yeah. Fine.
Yeah.
Okay. I think there are no more questions, and if somebody is interested, yes, we will keep your email ID open.
Yeah.
Information are in the chat box. They can email you and get the more information. So with this, we
And
have come to the end of this
and
session.
also
Yeah.
we look forward to his visit to the Asian Aerosol Conference. Hello, Dr. Mingzhou. Please
Okay.
come to the
I
Asian
will.
Aerosol
Yeah.
Conference.
I have interest to join to attend. Yeah.
Okay. Yeah.
Mhm.
Yeah.
And I think maybe Professor Chao Junji also will go there. I guess.
Yeah.
On
Okay.
behalf
Yeah.
of, yes.
Okay.
On behalf of IASTA, we thank you very much for immediately accepting in short time actually our invitation. Deliver this lecture. I think it is a very within I think 10 days or 15 days within that short time you are agreed, and we are grateful to have you on our online lecture. And also, as Dr. Maya invited, we are looking for you for the Asian Aerosol Conference in December, and we will host you. And thank you very much for giving this wonderful lecture. And anyway, we quickly we find out that this last part, these things are available in the internet or YouTube channel. I think other participants can go to, and in more detail, as Tanmay and others they are looking, they can take the video and they can. Thank you very much. Thank you.